In the last session we ended when we were with a discussion of geometrical optics and the geometrical regime, where the area where we can, the size of our wavelength, the optics, etc., allow us to treat our light as rays. But now we're going to talk about another approximation that we're going to use, and this is what's called the paraxial region. Many of the properties that define our optical system, what are referred to as first-order properties, are defined in what's called the paraxial region. The paraxial region is that region where the height of the ray above the axis is small, and the angle between the ray and the optical axis is also small. So in a region where we can say that the sine of theta, the ray relative to the normal at the point of intersection, is approximately equal to the tangent, which is effectively equal to the angle itself in radians, and that the cosine of theta, or phi, is approximately equal to 1. And again, we use this paraxial region to determine the first-order properties of an optical system, because this allows us to ignore the effects of aberration. If there are aberrations, it's hard to define exactly where the light comes to focus. But if we can ignore those effects, then we can define these first-order properties. So let's look graphically a little bit at what we mean by the paraxial refraction and paraxial region, and sort of look at light propagation. So although this is, let's say, not to scale, so we have some ray coming into our system, and it interacts at an index boundary. And here is the normal at the point of intersection. And again, if you want to think about it, if we're, let's say we have a lens very close to the optical axis, and we are very close to the optical axis, in a very small region around that optical axis, yes, there is curvature, but we can effectively treat the lens almost as being flat. We'll take into account its curvature, but for our purposes, I'm going to draw it as being flat. So here is the normal at the point of intersection, and here is this angle u, since the normal is, in this case, is parallel to the optical axis. The alternate interior angles are equal, so these are both the angle u. And after the ray refracts at the interface, it is now propagating in the new media with this index n prime at some angle n prime. And at the point where the ray interacts with the surface or intercepts the surface, it has some height y. Now, if we look at the calculations, so again, in the paraxial region, the tangent of u is approximately equal to the sine of u, which we can simply call u. We also have what's called the reduced angle, which is simply the index times the angle. And the actual power at a surface, remember, is the change in index divided by the radius, or times the curvature. And similarly, we have an optical thickness, like we have an optical angle, which is simply the thickness divided by the index in this particular case. Okay, so again, we can look at what happens when a ray intersects the surface, and we can sort of start with a Snell's law type approximation. So n prime u prime is going to be equal to nu minus y phi. And, or if we want to look at it in the reduced space, omega prime is equal to omega minus y phi. Similarly, y prime, the height as the ray travels in this new media, is a function of the height that the ray was when it entered in the media, plus the product of the thickness and the angle. Effectively, we're just propagating along this additional height, so we'll just use some basic trigonometry to determine what this additional height is. The key to these two equations, whether we use them in the physical form or the reduced or optical form, is when a ray hits a boundary, okay, the angle changes. But in the infinitesimal region around where the ray hits the surface, the height stays the same. The height changes as it propagates away, but the angle stays the same. So we can break ray tracing down into two fundamental processes. The ray hits an interface where it changes angle, or the ray propagates through a medium of constant index where the height changes but the angle stays the same. And these are what are referred to as our paraxial ray tracing equations. And we're going to be doing some homework problems, or you'll be doing some homework problems that will allow you to apply that to some simulations and understand how it all works. Another concept we want to talk about is what's called Fermat's principle. And Fermat's principle is going to come up several times over the next several weeks. It is the basis for geometrical optics. And what Fermat's principle, or Fermat's principle of least time, tells us is that the path traveled by a light ray from one point to another is that for which the time for the light to travel is an extremum. Now, extremum, of course, is a fancy word that says the first derivative goes to 0. So an extremum would be the shortest, the longest, but typically it's the principle of least time. It is that path for which the time is the minimum. There are some little cases where you can look at where you have other situations, but for our purposes, let's stick to calling it Fermat's principle of least time. So let's look at it sort of in a mathematical form. We have some light that propagates from some point P1 to P2. Let's assume we have some isotropic material. We define our materials as having an index of refraction, and let's assume for our purposes now that the index of refraction is simply the ratio of the speed of light in vacuum to the speed of light in a particular material. So if we want to find out the time it takes for the light to get from point P1 to point P2, we simply integrate over the speed of light over the path integral from P1 to P2, the index times the path, the direction vector. And the optical path length is simply we take the time out of that equation, and the optical path is simply the index times the integrated path, which goes back to what we were talking about right back here, where we have our path right here. The index times the angle. Okay? So we have our reduced thickness is simply the actual path times the angle. Let's take a look at a single refracted ray, and let's assume this is my point P1 here, and in my coordinate system it's going to have a z coordinate of 0 and some y value of y1. It makes an angle theta 1 relative to the normal at the point of intersection, where it intersects at point P, coordinate z, y of 0. And then we're going to calculate the distance down to this P2 here. And again, notice after refraction, because I have an index boundary, the path angle changes. The optical path is simply the index of refraction times the length of the ray path in the medium, plus this index of refraction times this ray path through the medium. And again, a little bit of trigonometry allows us to determine what those paths are. If we're dealing with Fermat's principle, we know that the time is an extremum, which says the first derivative goes to 0. So if I take the derivative of my optical path, and this is what it looks like, and I know this is equal to 0, which says this term must be equal to this term. And if I look at these two terms here and go back to the previous slide, we see that this is simply the sine of theta 1, and this is the sine of theta 2, which tells us that Snell's law, which tells us what happens as light propagates through our optical system, comes directly from Fermat's principle. So Snell's law tells us that the path of light, its direction vector, changes at an index boundary. The incident ray, refracted ray, and surface normal at the point of intersection all are located in the same plane. The change in angle is related to the change in refractive index, so n1 sine theta 1 equal n2 sine theta 2, or n1 over n2 sine theta 1 is equal to sine theta 2, because at an intersection this is our only unknown. And the refracted ray will be on the opposite side of the system of the surface normal. which we can see here. Okay, so here's the normal, closer to the angle, further away from the angle, but this is on this side of the normal, and this is on the other side of the normal. Okay, so that's enough for now, and we will continue again shortly. Thank you.